Bueno, buenos días. Buenos días. Hoy tenemos a Josefa Becerra, una de nuestras estudiantes aquí en el Instituto, que nos hablará del último artículo que ha publicado dentro del conjunto de MAGIC.
Hi. Hello. This talk is about proving gamma ray production in relativistic jets in flat spectrum radio quasars. First, I will briefly introduce in the Cherenkov technique and the MAGIC telescope before focus on the discovery of the flat spectrum radio quasar PKS-1222 in very high energy gamma rays with MAGIC and the physical interpretation of the results. As you may know, the very high energy gamma rays, which are defined for energies higher than 100 GeVs, cannot be measured from satellites due to the low fluxes. And we need the Cherenkov technique as a direct method for measure these kind of photons. The method is based in the interaction between the gamma rays coming from the space and the Earth atmosphere, which produce, as you can see in the sketch, a cascade of particles which travel faster than the speed of light in the medium and emit Cherenkov light, mainly in the optical range. So from this optical information we measure, we can infer the characteristic of the shower of particles and the incident gamma ray. This is the technique used by the MAGIC telescope located in La Palma. There are two telescopes working in stereo. And just a reminder, if you are driving in the observatory, please be careful with the car flashes, because it is, in fact, an optical telescope and disturb our observations. The energy range is from 50 GeVs to few TeVs, but we can go lower up to 25 GeVs using the special sun trigger, which is a Howard component of the telescope. The sensitivity is 0.8% of the gap in 50 hours. The energy resolution is 15%, and the angular resolution go from 0.1 degrees to 0.07, depending on the energy range. This source, PKS-1222, is a flat spectrum radio quasar, and it is the third object of this type detected in very high energy gamma rays up to now. The first one was 3C279, which have been already presented by Kastenberger in a previous talk, and PKS-1510. In the optical spectrum, we can see clear emission lines, which allow a measurement of the redshift 0.4, which means that this is the second most distant blazar detected in very high energy gamma rays with a well-measured redshift after 3C279. This is very important in the framework of the extragalactic background light studies. As you may know, the very high energy gamma rays can interact with the low energy photons from the extragalactic background, and via part production of electrons and positrons, and some of these very energy photons are absorbed. So the characteristic of this EVL are imprinted in the spectrum of the very high energy gamma rays. Also the redshift is very important in order to know what is the intrinsic spectrum emitted by the source. Otherwise, you don't know how the EVL is affecting to the spectrum. In this plot, we have the Fermi light curve for energies higher than 100 MeV. As you can see, the source is presenting a high variability of a time scale of 1 day. This is in 2010, from April to June. The vertical color lines represent the MAGIC observation. We start to follow up the source on 1st of May. We got some hint of signal. Well, in 3rd of May, for example, we got something around 4 sigma detection, but in physical and particle physics, the limit on the detection is set at 5 sigma for a robust detection. Up to only during the huge flare in Fermi of 17th of June, we were able to detect the source by first time. The observation time of the survey was 30 minutes, and the condition was not excellent in the sense that there was some moderate moonlight conditions. What later means that we have to use a bit higher cleaning levels, but still the energy threshold of the analysis is 70 GeVs, which is rather low for Cherenkov telescope. This is the theta square distribution, where theta square is defined as the square distance between the reconstructed position of the source in the camera and the expected position of the source. So if the signal is coming from this source, of course, this distribution has to peak around 0, as it is. And with the significance of this detection is more than 10 sigma. So it's a robust detection in just 30 minutes. Regarding the spectrum, in black point, the magic measure spectrum is represented. The spectrum covers from 70 to 400 GeVs. And for higher energies, we derive 2 upper limits. The gray shaded area represents the systematic error in the analysis, while the blue points represent the deabsorbed spectrum due to this EVL point. Well, for the point, the last EVL model from Dominguez 2010 is used, and the blue area represents the difference between different EVL models. As you can see, even the observed and the deabsorbed spectrum are compatible with a simple power law function. Let's see how the spectrum of this source looks in the Fermi energy band. The different colors, well, red, green, and blue, represent different states of the source in the Fermi band. As you can see, the typical behavior is that there is a spectral break from 1 to 3 GeVs. Well, the blue point is the spectrum measured during this huge flare where MAGIC detects the source. Let's see how we can combine in the spectral energy distribution the Fermi data and the MAGIC ones. In the left-hand side, we can see 2 points and 1 upper limit derived from Fermi data using just 2.5 hours centered around the MAGIC observation in order to be simultaneous data. Well, since the MAGIC observation is just 30 minutes, we cannot have strictly simultaneous data, but it is as much closer as possible due to the statistics. And it is compatible with the spectrum I already showed during a wide time windows. In the right-hand side, we have in black point the observed spectrum by MAGIC, and the solid blue line represents the deabsorbed spectrum using Dominguez 2010 EVL model, extend to lower energies. As you can see, this spectral shape is compatible with the spectral behavior I already present from Fermi with a cutoff around 2 GeVs, which means that a straight power law can describe the data from 2 to 400 GeVs. Regarding the time variation, given the stretch of the signal, we can perform a time variation study. In this plot, we represent the integral flux from MAGIC for energies higher than 100 GeVs as a function of the time. The gray point represents the flux coming from the background, and it is compatible with a constant flux, as it should be, while the black point represents the flux coming from the source. And of course, it is not compatible with a constant hypothesis. The doubling flux scale is around 9 minutes. Well, let's see how the canonical scenario of this kind of object looks like. Usually, we have a central black hole with an accretion disk, which is emitting in optical and UV, usually. Then we have the broadline region with some clouds, as you can see, which absorb and re-emit the emission coming from the disk. And further away, we have the dusty torus, which emits mainly in infrared. Also, we have the jet opening from the center, black hole, which is filled of electrons, and we have magnetic fields. And the main process that take place there is the synchrotron and inverse Compton scattering. This inverse Compton scattering can be due to can be produced in 2 different ways. Can be external inverse Compton, which means that the photon field Sorry. Well, as I told you, in the canonical scenario, we have we have synchrotron and inverse Compton. The external inverse Compton is due to the interaction between the electrons and the relativistic electron and the external photon field. And the self-synchrotron Compton is due to the interaction between the electrons and the photons produced in the synchrotron process. And typically, what we consider is that the whole section of the jet is emitting via this process. And the gamma rays are coming mainly due to the inverse Compton scattering. Let's see how we can explain our spectral energy distribution in this canonical constant. Well, there is 2 possibilities. The emitting region can be inside of the broadline region. And in this context, we have to have 2 main considerations. One is, at such high energies, we are working in the Klein-Shiner regime and not in the Thomson one. That means that the efficiency of the process is lower than in the Thomson. And the absorption due to ultraviolet photons in the redline region. With these 2 considerations, we expect a cutoff around few GeVs. Or, in the other hypothesis, is we can consider the emitting region outside of the broadline region. In that case, we have still the Klein-Shiner effect, but the photon field is not ultraviolet, but infrared ones coming from the dusty torus. Since we don't see in our set any cutoff, a few GeVs, we can directly exclude the first case, and the emission should come from outside of the broadline region. In the case of the time variability, as I explained, there is a fast variability of the source, which means that the emitting region should be rather small. So if we consider the standard view of the jet opening from the central black hole, this emitting region should be rather close to the black hole, which means that the emitting region should be inside of the broadline region. So this result challenged the canonical scenario, because the same emitting region cannot be at the same time in 2 places. So There is two main possible solutions. One is a very strong recollimation of the jet with a low cross-section of the jet, small, far away from the central black hole, or maybe it suggests that there is substructure in the jet, something like small blobs or small mini-jets inside. We started to work in this second hypothesis, and we consider the two emitting regions. One is the whole section of the jet, which will account for low energy emission, and the gamma ray emission will come from this small blob from here. Both of them of this region will emit in synchrotron, self-synchrotron Compton and external Compton. In the case of the small blob, the external Compton will be due mainly to two photon fields. The first one will come from the infrared coming from the torus, and another extra photon field will come from the whole section of the jet. Here we have a set of this object, taking into account more multi-wavelength data. And the blue line represents the emission coming from the small blob, which accounts for the gamma emission. And the red line represents the emission coming from the whole section of the jet. And as you can see, it fits quite nicely, the data. What we found also is that this interaction between the small blob via inverse Compton with the photon field created in the whole section of the jet is not important. The main process is the inverse Compton due to the torus photon field. So these two regions can be separated. Of course, the small blob have to be anyway outside of the broadline region, otherwise we don't expect very high energy photons. They could not escape from the broadline region. But the whole section of the jet could be even inside of the broadline region. And again, this consideration, this new scenario, can account for the set of the source. Well, just some final remarks. This detection of Flat Spectrum Radio Quasar, Egt100 was observed during a high state in the GeV band from 70 GeVs. The combination between MAGIC and Fermi data covered from 0.1 to 400 GeVs. And the most important point is that they are simultaneous, so allow this kind of studies. The intrinsic spectrum is compatible with a simple power law from 2 GeVs to 400 GeVs and present very fast variability. And these 2 points together challenge the standard one-zone emission models, but can be well described by 2-zone emission models. That's all. Thank you.
Very nice results. How do you estimate the torus emission at the jet location?
Well, we consider standard values. I mean, it's not the values for this source.
And how critical is that in the fitting of the CD?
Well, in fact, the problem with these two-zone scenarios is that there is too many free parameters because you have 2 different regions. So there is a wide range in which you can anyway adjust this data. I mean, it's not, we cannot just give a number. Just it's a possible scenario which can describe but it is something, say, to propose a new scenario. It's not a matter of numbers. But what is for sure is the one-zone emission model cannot work with this result. It's work on process also.
Thank you.
Hi. I just remembered something. FSRQ also has this structured jet model, you know, where you have a spine and a layer, outer layer in the jet, you know, which we use for M87, for instance. Do you know it, or you don't know about that?
Well, not. I just work in this.
The block, yeah. Because there you can also get very hard spectra, and I was wondering if you or Fabrizio tried to use this other model to explain this emission.
Well, in principle, of the model up to now, in which Fabrizio is working, cannot describe this data. That's why we start to think about in a new view.
Okay.
Well, first of all, let me thank you for the very nice talk. Can you go back to the slide where you show the two-zone model, please? Thanks. This one. Yeah,
this
no,
one.
This one. Right. Would other wavelengths help in supporting this model as opposed to other models, like if you had spectra in the visible or radio observations?
Yes, for sure. As much data you have, it's better. But the point is, the important thing is to have simultaneous observation. And this is very challenging to catch this guy, because only you can see it when it is in first state. And we are triggering the observation with Fermi data. But typically, the time scale is 1 day as longer. Well, we have some more flare longer, but usually the time scale is too short. Even if Fermi is scanning the sky every 3 hours, once you have the analysis of the data, it's 1 day later. So maybe the flare is already gone. So you can measure what is the status of the source, not in the flare status. So, I mean, it's good to have data, but still, if it is not simultaneous, you can, I mean, or we need let's say, follow-up of the source every time, or otherwise we cannot catch it. So the other wavelength cannot be really used in constrain the model. It's a bit difficult. But what is for sure very useful is to measure the redshift. I mean, without the redshift, and it is from optical observation. And there is a lot of, well, quite a lot, source emitting in very high energy gamma rays, which with the redshift is unknown. So first, we cannot know the intrinsic spectrum, so you cannot model it, the emission. Or you cannot use it in order to study this EBL. So it's really important to follow this, I mean, to estimate the redshift of these kind of sources.
What is the problem of getting the redshift of a source? It's because the box, I mean, the location is not particularly good, or?
Oh. It depends on which kind of source we are talking about. In the case of Flat Spectrum Radio Quasars, we have, as you saw in the first slides, we have very nice emission lines, so it is fine to measure the redshift. But in case of BLAC objects, you are seeing across directly to the jet emission. So you have some constant emission, but you cannot see the lines. So it's very difficult. In this case, you have to try to observe the source in an optical low state in order to be able to see this line. But a telescope like Grand Tecan or this kind of big telescope only are able to do that. for such far away source. That's my proposal for optical observations.
But in this particular spectra you have shown for this source has been taken where? This is from where? From what telescope?
Oh, I don't know the telescope. It was published. I mean, it's not mine.
Right.
But this is a flat spectrum radio quasar, and in this particular case is of source, but well, the redshift is not a problem, the determination. But this kind of sources is only 3 sources have been detected in very high energy gamma ray. The real problem is the BLAC object, where we have to use this big telescope and different approach.
Because that has to do with Alessandro's question. I mean, that if you could make a follow-up of simultaneous observations in the optical, for instance, may be useful. And in this particular case, I don't know how bright is the source, also what is the typical observing time you will require to get the spectra in the optical for this target. Maybe it's short. I mean, you don't need that much time. And I don't know, maybe I'm saying silly things. The question is, would it be possible that any of the medium-sized telescopes at La Palma would take spectral, optical or infrared spectra of these targets?
Yeah, for this, yeah. We are following with KVA telescope in La Palma most of the sources observed by MAGIC. So the optical flux is not a problem. The real problem usually is the redshift. But we have data